Deep inside our world, something just changed direction. This shift did not happen on the sun-drenched surface or in turbulent atmosphere, but in the profound, eternal darkness over 3,000 miles beneath our feet. At the very heart of our planet, a massive sphere of solid iron, a world unto itself, has altered its primordial rhythm. This sudden change at Earth's core could be the part of a slow, majestic cycle that subtly influences the very fabric of our surface existence, from the length of our days to the integrity of the magnetic shield that protects all life. We're embarking on a journey to a place no human eye will ever see. A realm of such extreme pressure and sun-scorching heat that it defies imagination. Picture a solid ball of metal, spinning in the silent, crushing dark, isolated within a sea of fire. This is Earth's inner core, a behemoth larger than the planet Pluto, and recent seismic detective work suggests it has not just slowed its independent spin, but may have begun a gradual reversal, turning the other way relative to the rest of the planet. Why would the planet's heart change its beat? What forces could possibly command such a colossal object to alter its course? And most pressingly, should the surface world, our world, even tear? The answers are not simple, but are instead buried in over a century of brilliant deduction, stubborn anomaly, and technological serendipity. A testament to humanity's quest to understand the ground beneath. I'm your host, and this is Winds of Come. To truly grasp this profound mystery, we must first descend, layer by layer, on a conceptual journey to the planet's fiery center. Our starting point is the thin, fractured crust upon which we build our civilizations. This brittle shell is a dynamic, shifting mosaic. Beneath this crust lies the mighty mantle, a vast expanse of solid rock that behaves like slow-motion putty, the engine of plate tectonics. Deeper still, we cross into the outer core, the churning, swirling sea of liquid iron and nickel, a turbulent, electrically conductive fluid. This complex, chaotic motion of liquid metal is the source of Earth's magnetic field through a process called the geodynamo. It is this invisible shield that deflects the constant barrage of charged solar wind and cosmic radiation, carving out a protective bubble in space without which Earth's atmosphere would be stripped away and life as we know it would likely not exist. And suspended at the very center of this liquid metal maelstrom, we finally reach our destination, the inner core. A colossal sphere with a radius of over 1,200 kilometers. It is composed primarily of crystallized iron under such a... It is a pinprick on an apple's skin. The entire concept of a layered Earth with a metallic core was, for centuries, pure speculation. The breakthrough, therefore, came not from direct observation, but from learning to become planetary physicians. We learned to read the planet's own violent shudders, earthquakes, as a doctor uses X-rays or ultrasound to see inside a body. Our modern understanding began not with waves, but with weight. In the late 19th century, physicists and geologists were puzzled by a fundamental property of our planet, its density. By observing Earth's gravitational pull, scientists calculated an average density of about 5.5 grams per cubic centimeter. Yet, the rocks we could collect from the surface had a density of roughly half that. A simple theory suggested the planet was compressed into denser rock towards the center. However, physicists like Emil Vickert realized a critical flaw. The numbers simply didn't add up. The planet had to be made of something different, something far denser in its heart. The inspiration for a solution came, ironically, from the heavens. Scientists had long studied meteorites. Among them were iron meteorites, lumps of almost pure nickel-iron alloy. Wiechert reasoned that our planet's interior must be organized by chemistry. He postulated a massive, dense metal core, hidden deep within a rocky silicate shell. This core would account for the planet's overall heft, like a lead weight inside a foam ball. It was a stunning guess, but it needed physical, observable proof. That crucial proof arrived with the modern seismograph. These instruments began to catch the faint encoded whispers of distant earthquakes. A pioneering geologist named Richard Dixon Oldham made a critical and systematic observation. The squiggles on the paper, or seismograms, showed not one chaotic signal, but 3 distinct wave packets arriving at different times. He identified and named them. The first, fast-moving compressional waves, which he called primary or P waves. These were followed by slower secondary shear waves, or S waves, and finally by the large rolling surface waves that cause most of the destruction. Laboratory physics had established a crucial difference. P waves can travel through both solids and liquids, but S waves cannot propagate through fluid mediums. They are simply absorbed. Oldham noticed a pivotal pattern. For earthquakes on the opposite side of the globe, the S waves were significantly weakened or entirely missing. This was the smoking gun. His monumental conclusion was that our planet must possess a central core that behaved like a fluid. The liquid outer core had been discovered, not by sight, but by its shadow, by the seismic waves it erased. Yet the story was far from complete. The plot soon thickened with a puzzling and persistent anomaly. Decades later, a brilliant, meticulous, and famously formed this solid inner sphere would have different seismic properties. It would act as a new lens, refracting some of the P waves a second time, bending them back into the shadow zone and perfectly explaining the anomalous signals. She had seen the critical signal hidden in the noise that others had simply walked past. With this stunning deduction, the full layered picture of our planet's hidden heart came into focus. A solid inner core nested within a liquid outer core, surrounded by a malleable mantle and wrapped in a brittle crust. It was a triumph of pure reasoning, but this clearer picture immediately gave birth to a profound and tantalizing new question. This solid metallic sphere floats, suspended and isolated, in a seething, turbulent sea of liquid metal. Is it locked in step, rotating as a rigid part of the whole planet? Or could it spin independently, like a gyroscope within a fluid housing, marching to its own beat within its liquid cage? The implications were staggering. To find out, scientists needed a natural laboratory and an unprecedented level of precision in global seismic data. They needed to measure the unseeable movement of an object buried under 3,000 miles of rock. Ironically, the fierce geopolitical tensions of the Cold War provided the necessary technological leap. Peering covert underground nuclear tests by rival superpowers, the United States launched a top-secret program in the 1960s called Project Vela Uniforme. Its mission was explicit: develop a global, foolproof system capable of distinguishing between the seismic signatures of natural earthquakes and clandestine nuclear explosions. This national security imperative drove a massive investment, over $500 million in today's money, into seismographic technology. It funded the development of more sensitive instruments, and most importantly, created a coordinated worldwide network of listening posts. For pure seismologists, it was an unexpected bonanza. The planet was suddenly instrumented with an array of ears finer than ever dreamed of for science. With this new treasure trove of data, researchers could now hunt for rare earthquake doublets. These are pairs of quakes that originate from virtually the same subterranean location, but are separated by years. If the inner core rotates independently, seismic waves from the second quake would pass through this slightly reoriented inner core. The subtle change in crystal alignment would cause the waves to arrive at distant stations with a minutely different travel time, or a slightly altered waveform shape compared to waves from the first quake. It was like using the inner core as a giant, slow-turning cogwheel, and earthquake waves as a sub-millimeter precision caliper to measure its rotation. The hunt was computationally intense, requiring algorithms to sift through decades of data to find these seismic twins. But persistence paid off. By 1996, a team from Columbia University, led by seismologists Paul Richards and Xiaodong Song, struck gold. Analyzing a sequence of doublets from the remote South Sandwich Islands, they found a consistent, tiny but statistically significant increase in the travel time. Their landmark conclusion was electrifying. The inner core was indeed rotating, and it was spinning faster than the mantle and crust above us, a phenomenon they termed superrotation. It was the first direct observational evidence that the heart of our planet has its own distinct rhythm. This groundbreaking discovery threw open the scientific floodgates. The new field of study exploded. But as more teams applied similar and new methods to different data sets, a confusing and contradictory picture began to emerge. Some subsequent studies in the early 2000s confirmed the superrotation. Others came to the opposite conclusion, proposing that core was actually spinning slower than the mantle, a subrotation. Yet other research suggested the spin rate wasn't steady at all, but fluctuated on much shorter decadal timescales. For a period, it seemed the scientific community couldn't agree on most basic facts. The resolution to this perplexing conflict has come from the very latest wave of research. The key insight is that the inner core isn't spinning at a constant rate. Instead, its motion is oscillatory. It speeds up, then slows down, pauses, and actually reverses direction, following a 70U rhythm. The seminal 2023 study from researchers at Peking University analyzed the subtle waveforms of seismic waves from the 1990s through the 2020s. Their sophisticated model argued that the inner core's superrotation has nearly paused in recent years and, relative to our surface reference frame, has begun a very slow backward drift. Crucially, they noted that a similar reversal likely occurred in the early 1970s, cementing the idea of a cyclical, back-and-forth wobble rather than a one-way superrotation. It would be like a runner on a circular track, alternating between being ahead of and behind a slower runner, periodically lining up side by side. By analyzing over 120 repeating earthquakes, they found these moments of seismic echo where the waveforms matched perfectly because the core was back in the same alignment. The latest synthesis of this research suggests we are currently in one of those pivotal transition phases. The great planetary pendulum is at the peak of its swing. Beneath our feet lies a world of unimaginable heat and pressure. But what secrets is the Earth's core keeping from us? The inner core is a solid sphere of iron, roughly the size of the moon, suspended within a sea of molten metal. For decades, it's been known to spin faster than the planet itself. But recent seismic data reveals a shocking new trend. The inner core's rotation is slowing down. It is now nearly at a standstill and may even be about to reverse direction. This slowdown is a vital part of the geodynamo that generates our planet's magnetic field, a shield that protects all life. As the inner core changes its rotation, we are reminded of the powerful, unseen forces that continue to shape our world. This profound shift at the absolute center of the Earth is not an isolated, academic quirk. Its subtle signature is written, in faint but detectable script, into the fabric of our surface world. The implications are real and measurable, though their scale is often tiny to human perception. Scientists have carefully linked this proposed 70-year core oscillation to minuscule but systematic variations in the length of our day, on the order of a few milliseconds over decades. The planet's rotation speed is not perfectly constant. It fluctuates due to changes in atmospheric winds, ocean currents, and movements in the Earth's interior. The gravitational coupling between the mantle and inner core is one contributor to these length-of-day variations. Furthermore, the same cycle appears to correlate with measurable, long-term fluctuations in the strength and directional wander of Earth's magnetic field, which itself is generated by the outer core's motion. Changes in the inner core's rotation could influence the fluid dynamics of the outer core above it, tweaking the geodynamo. Intriguingly, some climatologists and geophysicists have also identified statistical correlations between the phases of this deep Earth cycle and long-term, small wavelength trends in global mean surface temperature and sea level rise over the past century. It seems the core's rhythm may have a whisper-thin influence on the planet's thermal budget, and perhaps the transfer of heat from deep interior to the oceans. But here is the crucial point that must be emphasized. This core oscillation is a natural background planetary oscillator. It is not the driver of the rapid, dramatic, and unprecedented global warming trend we have observed since the mid-20th century. That dominant, overwhelming signal comes unequivocally from the immense volume of greenhouse gases humans have added to the atmosphere through fossil fuel combustion and deforestation. The core's rhythmic influence is a faint, deep bass note in the planet's complex climatic symphony, now completely overshadowed by the much louder human-caused crescendo of warming. Recognizing and understanding its deep Earth rhythm is about refining our models, leading to a more nuanced understanding of Earth as an integrated system. The entire story of the inner core is a breathtaking testament to As Inga Lehman herself remarked late in her long and illustrious life, reflecting on her discovery, the first results for the properties of the inner core were naturally approximate. Much has been written about it, but the last word has probably not yet been said. Her humility remains prescient. The journey is far from over. New technologies promise even deeper insight. Distributed acoustic sensing, DS, is turning existing fiber optic cables spanning oceans and continents into dense arrays of makeshift seismometers, capturing ground motion with unprecedented detail. More powerful supercomputers are running sophisticated simulations of the geodynamo and inner core dynamics. Future analyses of growing seismic datasets may reveal more layers within the inner core itself, more complexity in its crystalline structure, and a more precise understanding of the forces driving the magnetic engine that makes our world habitable. The journey to the center of the Earth continues, not with drills, but with ideas, data, and an unending desire to comprehend the magnificent and dynamic planet we call home. So, what do you think? Is this planetary heartbeat something we should monitor more closely as a vital sign of Earth's internal health? Could a deeper understanding of this cycle help us refine long-term models for Earth's magnetic field, which is crucial for satellite and communication technology? Or does the sheer scale and slowness of it put it in the realm of pure, all-inspiring science? Let me know your thoughts, questions, and theories below. If this journey into the deep Earth fascinated you, help us explore more of science's greatest mysteries. A like on this video truly supports the channel Winds of Thought, helping us dive deeper into the stories that shape our understanding of the universe. Consider subscribing to join our community of curious minds. Thanks for thinking with us.